So the next paper in our sequence of effects is effects and coeffects in call by push value. The talk will be given by Emmanuel, Suárez, Acevedo.
Cool. Hey everyone, I'm Emmanuel. Feel free to call me Emma. This is work I was involved in while completing a master's at Penn. I am now a PhD student at Cornell. So let's talk about effects and coeffects in call by push value. To start off, I thought we'd have a motivating example. So for this bit of code here, we might ask ourselves, can the first line be removed as a compiler optimization, namely dead code elimination? And for this example, the answer is yes, right? We're not really doing anything in this first line. We're just binding the string hello to x, and we're not using x anywhere. So we can get rid of this line. This would be fine. We wouldn't be changing the behavior of the program. However, let's consider this slightly different program where we're saying let x be print hello. As a programmer, I'd probably expect this program to print hello and then print world. And if we were to get rid of this line, we'd actually be changing the behavior of the program. So although x isn't used anywhere, suddenly we can't actually kind of get rid of this line. And we can kind of ignore these two pieces and just sort of ask ourselves two questions to say, can we get rid of this line? The first one being, is the code bound to x pure, here E1? And the second one being, is x unused in the code that follows? So is E2 actually kind of using x? And because we're talking about a compiler optimization, our goal is to be able to track this statically at compile time. And for that, we're going to be looking at augmenting our type systems. So let's start with effects, considering now this different program where in this typing judgment where we have the program print x, and we're saying that it's well typed as long as x is of type string. And I threw in an extra y in there because why not? And although we kind of have this idea that this program is well typed, there's this additional notion, right, that there's going to be some sort of output here. And this is information that we also want statically, right? There's a behavior that's observable. And for that, we might augment our type system with some sort of I/O effect information and say this program may have some sort of output effect. And really, we can kind of abstract this away to any structure that's an observable behavior. So now this program may have an effect phi, because we don't only want to talk about I/O effects, but also about running time, right? So how much time might this program take, or exceptions. And then on the other hand, we have coeffects. And if you've never heard this word before, anywhere that you see the word coeffects, you can kind of change it for demands, because that's really what a coeffect is the demands that a program is making on the world around it, and in particular on its inputs. So now let's kind of look at the inputs of this program. So the variable x and the variable y, we kind of are able to kind of talk about this relevance coeffect. So is this input relevant to my kind of program? And in particular, x is relevant because it's used, but y is irrelevant. And we could also augment our type system with this information statically, where we're saying, there should be a 1 in the x that isn't showing up there, but where we're saying that there's kind of this coeffect that we're demanding from x and we're making no demands of y. And really, we can also kind of abstract this away again to say we're making some abstract demand q1 from x and some demand q2 from x2 because we want to talk about different coeffects. And before I kind of talk about those, we also can just extract all of these demands to just some sort of vector of demands, where now we're making demand qi on the variable xi of the context. And we do this because we don't only want to talk about relevance, but more generally we could talk about resources. So how many copies of a variable am I demanding? Or differential privacy. So how sensitive is a function going to be to its inputs? Or information flow, where I'm sort of demanding a confidentiality level to be respected by variables. And now, kind of revisiting this question from before, we can sort of identify these two questions as statically tracking the effect of E1 and the coeffect that E2 is kind of demanding of X. And there's kind of this one little bit here that's a little tricky, which is that question of statically tracking effects, right? So I've kind of ignored what programming language this is. Maybe you looked at it and thought it was OCaml. And if it were OCaml, we could ask ourselves, what's the expected effect of this program? And the answer would be that we run through this first line and we print hello, and then we bind x to unit, and we substitute x with we substitute x with unit. However, if maybe you like writing Haskell, then there's this kind of additional option here where in the first line what we do is we take this line and we actually bind x to the code that says print hello, right? And in the second line, we instead substitute x with print hello twice and end up printing hello 2 times, and we'll have hello printed 2 times. I don't know why my slides aren't working super well, but the expected effect here would be hello twice. So instead of kind of having these questions of kind of what is the expected effect of the program, our goal is to instead use an intermediate representation, right? Because we're talking about compile time optimizations. And in particular, we want to be able to talk about both of these behaviors, right? Printing hello once or printing hello twice. But we also want this intermediate representation to have an explicit evaluation order because we actually do want to have only one answer to the question, what is the expected effect of this program? And this brings us to call by push value, which is a programming language that has been referred to as a subsuming paradigm because it allows us to talk about many behaviors at the same time, right? Both of these behaviors that I just went through, where we can take this program and we can translate it to call by push value so that we print hello once, or translate it to call by push value so that we print hello twice. And this has made call by push value a very nice intermediate representation because it can talk about these behaviors while also being very explicit, because a nice thing about call by push value is that for both of these programs, there's only going to be one answer to the question, what is the expected effect? And the main idea behind call by push value is that it takes expressions and it splits them into values and computations. And Paul Blaine-Levy, who came up with call by push value, says that you can think of this as kind of a value is, so a string is a value, and a computation does. So printing a string is a computation. So to kind of go over what call by push value is in more detail, why not actually just take this program and translate it to call by push value 2 different ways, right? Print hello once and then print hello twice. So let's start out by printing hello once, where we take this first line and we translate it with this left arrow syntax, where this left arrow is sort of a sequence. And what the sequence operation does is it takes a computation of type funit, where f is this sort of returner type marker, saying that I will return a value of type unit. And the sequence operation binds the value returned by this computation to the variable x. And afterwards, we kind of keep on going with kind of the rest of our computation. And this is what a call by push value program is going to be in the end, is a lot of sequence computations. And the kind of remainder of our program is a translation of the next line. So kind of let's move on to that, where we're sequencing x with itself. So why not try sequencing x again using this sort of sequence operation. And there's this one issue here where x is a value. So what we want to do is kind of add this syntax that says return x, so that we're saying take this value x and do the computation of just returning this value. And now we have a complete call by push value program, so we can ask ourselves what's the expected effect of this program. And if we run through it, in this first line, we're going to print hello and bind x to unit, and then substitute x with unit 2 times and complete our program. However, like I said, we can compile call by push value a different way, where now we want to print hello twice. So let's do that. We go through this first line and we use sequence again, but now we add this sort of kind of curly brace syntax, which means suspend, where I take this computation of type funit and I suspend it to this kind of suspender type marker that says this is a value of type ufunit. And this is a value, so let's kind of say return this value. And now we kind of have this idea from before where we're saying I'm returning the code that says print hello. So moving on to the next line, we translate it with sequence again. And as before, x is a value, but really what x is a suspended computation. So we don't want to return it now. What we want to do is add this bang syntax that means force, that takes this suspended computation and forces it to be its underlying computation and actually kind of runs that computation. And now we have kind of we have a complete program again, so let's ask ourselves what the expected effect of the program is. where we run through this first line and we bind x to the code that prints hello that's been suspended. And the second line, we substitute it and we actually force this suspended computation. And then we print hello and return unit. And we end up doing the same thing in the third line, printing hello twice. And this is kind of the nice thing about call by push value, where we were able to translate this program two different ways and talk about these behaviors while still kind of having a very explicit answer to what is the expected effect of this program. So we don't try to kind of answer this question of dead co-elimination in this kind of random language. Instead, we talk about it in call by push value, where we take call by push value's type system and we annotate it with effects. Where we kind of use this epsilon here to mean a pure effect. And this type system is very similar to kind of existing type and effect systems for call by push value. But what we do in our paper is we also annotate this type system with coeffects to ask ourselves, is there some demand being made on M? So is X unused in N? And this gives us this kind of new typing rule in our system that's kind of justifying this dead code elimination, where looking at this demand here, we see that it's ignored. So although M is demanding gamma 1, in our final conclusion, we actually can ignore the demand made by M because M is discardable. So we kind of take this, this actual kind of code here and prove that it is in fact equal to N, which in practical terms tells us that for pure unused computations, it is in fact okay to kind of discard them, and dead co-elimination is correct. And this is a result that's been mechanized in Coq as well as have been the rest of our results in our paper. And we prove this equivalence with respect to the following semantics, where we take a computation in some environment, mapping variables to values, and we evaluate it to a terminal result. And we annotate it with an effect, which is the resulting effect from this program. And we annotate it with a coeffect, which is the consumed coeffects of the program. So this program will consume 5 resources, for example. And we take call by push values type system that we've annotated with effects, and we relate this type and effect system to our semantics, where we're kind of providing an upper bound to the effects that will happen at runtime. And it's an upper bound because we might have branching and we might print in one branch but not print in the other. And we do the same thing for coeffects, where we also kind of say, that if we have a demand that we're making on M, that is enough. In fact, or those are the coeffects that will be consumed by the computation. And call by push value ends up being a really nice language to talk about effects and coeffects in particular, because it gives us this very clean separation. So, for example, we kind of are able to annotate our U types with effects, where this is the kind of suspended effect of a computation M. And we're able to annotate our F types with coeffects, where this is kind of the multiplied coeffect. So if V is demanding gamma, then if I use V Q times, for example, I need to multiply that demand by Q. And additionally, speaking of those compilations that I showed before, we prove that they preserve effects and that they preserve coeffects, kind of showing us that it's reasonable to talk about the effects and coeffects of a program in call by push value. And there's a lot more in our talk, but that's kind of some of the main ideas. And thank you very much for your time, and I'd be happy to take any of your questions.
Great. Questions? Yes.
Sorry, what's it?
What effect does adding the effects and coeffects have on the equational theory of call by push value? Do you have more equations or fewer?
Well, we don't really work with call by push values equational theory per se. We kind of work with our own semantics, so I can't really answer that question.
Maybe a follow-up to that. Excuse me. It looks like when you say that M sequenced with N is equal to N, that this is an equational. This is a kind of equational theory.
Yeah,
right?
yeah. I'm using this syntax to kind of as like syntactic sugar for saying that And so we have kind of a semantics that we have in our paper, which is a semantics that actually discards unused computations. And we have a normal semantics, which just says, I'm going to actually not discard this computation. And we prove this result that basically both of these will result in the same value and have the same effect and have the same demands, the same coeffects. So that's kind of what this equivalence here means, just because it would be too much like different notation in one slide. Yeah. So the kind of equations that we do are with respect to the semantics here.
So I was a bit surprised about the semantics you say that the Haskell code has.
Yeah.
I don't think that's how Haskell works, right?
Yeah.
You're missing a do keyword or something.
Right. Yeah. I'm using Haskell as so really I'm talking about a call by name and a call by value semantics,
yeah.
But since I had like real code just relating it to an actual language that sort of is call by name, but it isn't actually like good Haskell or correct Haskell code that you might write.
Well, Haskell wouldn't behave like that unless you put this statement in a do expression, right?
Right.
For
yeah.
the particular case of the IO monad.
Yeah. Exactly. Yeah.
Okay. Maybe a more straightforward comparison could be made with Scala, where val binds call by value binding, whereas def binds a call by name value. So you have both in the same language.
Yes. Yeah. I was looking for an example that would translate nicely to call by push value. That might have been a good one.
Mm-hmm.
Yeah.
Okay. Thanks.
I feel like this might actually be close if you interpret your semicolon kind of as a do.
Yeah. Yeah.
That's how I looked at it.
Right. Yes. There's like, if you're thinking of it as Haskell, there's going to be like a do there, and you're going to use like Haskell's like sequence, like function that sequences like the monad.
Yeah, sequence is a different thing. If you use that, if you use sequence, then actually you get call by name, call by need. So you're not actually going to print twice.
That's fair. Yes. Okay. Yeah. Okay. Yeah. I mean, it's more the example to kind of just motivate that we have call by need semantics and call by value semantics, or in real languages. Yeah.
All right. Well, maybe the next speaker can come up while we take maybe one more question. If there is one. So actually, one question I had was thinking about. So you talked about this theory and how you can use it to, for example, eliminate dead code. Do you envision that just as sort of underneath the hood in an ordinary in a programming language for within a procedure, or would you see this as something where you would add the types to the language to do reasoning across procedures and so on as well, and what might that look like? You have effects and coeffects in signatures then, right?
Right. Yeah. I'm not sure I understand the question entirely. Could you repeat it maybe?
I'm just thinking about what. Have you thought about what this looks like in like a service language?
Yes, right. So this is kind of a motivation, but we focus entirely on the meta theory, and some interesting future work would be kind of just an actual surface language that we're kind of elaborating into call by push value. Yeah. Is that?
Yeah.
Yeah.
Sure.
Cool.
All right. Thank you. Let's thank the speaker again.